Now let's derive the torque equation. For this, consider a shaft fixed at one end and it is twisted at the other end. Shaft of length L and radius R. So to derive the torque equation, we consider a shaft of length L and radius R. The shaft which is fixed at one end and torque is applied, or the twisting moment, it is applied at the other end. So in order to derive the torque equation, we consider a radial line drawn on one end face of the shaft. A radial line drawn on one end face of the shaft. Due to this twisting moment or the torque, this line is displaced to an angle theta. This line is displaced to an angle theta. So the length of the arc produced by this displacement is equal to r theta. Now similarly, consider a line drawn parallel to the axis of the shaft. Due to this torque or twisting moment, this line is displaced to an angle gamma. The angular displacement of this line is gamma. So length of the arc is equal to L gamma. Assuming that both the length of arcs are equal, we have L gamma is equal to r theta. So from this we have gamma is equal to r theta by L. So this is equation 1. So from the basics of stress strain theory, we have shear stress tau represented by tau is equal to shear modulus into shear strain. So this equation holds till the component is elastic. So from this, gamma can be written as tau by G, where G is the shear modulus, tau is shear stress, and gamma is the shear strain. This equation is valid for as long as the component is elastic. So from this, substitute the value for gamma. This is equal to tau by G is equal to r theta by L. So this can be further written as G theta by L is equal to tau by r. This is equation 2. So from this equation, it can be seen that shear stress is proportional to the radius. It is maximum on the surface. So this equation can be applied to any radius. So from this, G theta by L is equal to tau by r, where r is any radius. So now consider an elementary ring at a radius r. So this is the radius capital R, and to derive the torque equation, we consider an elementary ring of area dA at a distance of r, small r. So this is the elementary ring dr. So now when torque is applied onto the shaft, the internal stresses resisting this torque, it can be given as, this is the elementary ring of area dA, it is given by 2 pi r dr. So the shear stress tau acting tangential to this ring is tau. So the force acting dF is equal to tau into area dA, which is equal to tau into dA, area of the ring, is 2 pi r dr. So dF is equal to tau into 2 pi r dr. Now the torque acting on the ring is dt, that is equal to 2 into 2 pi r into r dr. At a distance of small r, the torque acting on the elementary ring is equal to 2 pi r into r dr. So from this we have tau 2 pi r square dr, dt is equal to. So substitute the equation for tau in this expression, that is dt is equal to tau is equal to g theta by L into small r 2 pi r square dr. This finally gives g theta by L into 2 pi r cube dr. Now when the torque, it is acting on the whole cross section, we integrate this equation. So finally we get, on integrating, torque acting on the whole cross section is equal to g theta by L integral 0 to capital R, acting on throughout the whole cross section, 0 to R, 2 pi r cube dr. So this is the polar moment of inertia, which is the ability of a material to resist this twisting moment or torque. Higher is the polar moment of inertia, more is the resistance to twisting moment. So this is indicated by the symbol J, which is known as polar moment of inertia. So from this, torque is equal to g theta by L into J, that is polar moment of inertia. So we have the equation now, T by J is equal to g theta by L. So this is the equation for the torque, whereas g theta by L can also be written as tau by R. So T by J is equal to g theta by L, where g theta by L can also be written as shear stress by the radius. So this is the equation for the torque, which is valid for only elastic strains. Now we have seen about the equation for the torque. Now what is the state of stress of an element when it is subjected to torque? Two axes, longitudinal axis X and transverse axis Y. The state of stress is biaxial. We have normal stresses sigma 1 and sigma 3, which are equal in magnitude but opposite in sign, and maximum shear stress, which acts on planes perpendicular to the longitudinal axis and parallel with the longitudinal axis. So this is the state of stress of an element subjected to torsion or the torque twisting moment. So the state of stress is biaxial. Sigma 1 is the normal stress, which is tensile, and sigma 3 is the compressive stress. Both are equal in magnitude but opposite in sign. It is the tensile stress and sigma 3 is the compressive stress. And tau max is the maximum shear stress, which acts on planes perpendicular to the longitudinal axis and parallel with the longitudinal axis. So these are the planes over which maximum shear stress acts, perpendicular to longitudinal and parallel with the longitudinal axis. And this normal stress is equal in magnitude to that of the maximum shear stress. When a ductile material, it is subjected to a torque, it fails by torsion. The plane of fracture it is perpendicular to the longitudinal axis, because this is the plane of maximum shear stress. So this is how the failure looks for the case of a ductile material. It fails along the planes of maximum shear stress, which is perpendicular to that of the longitudinal axis. Whereas a brittle material fails in torsion along the plane which makes an angle 45 degrees to the longitudinal axis, because this is the plane over which the maximum normal stress acts, that is sigma 1. This is the plane over which the normal stress, tensile stress, is acting over that plane. So this is how the failure for the case of a brittle material which fails in torsion. The failure, it appears to be like that of helical fracture, and this is for the case of ductile material. So this is the plane over which the brittle material fails, because to this plane the maximum normal stress, which is the tensile stress sigma 1, is acting on that plane. So this is about how a brittle material fails in torsion and the ductile material fails in torsion, which is the maximum shear stress that is perpendicular to the longitudinal axis for the case of ductile, and for the case of brittle it is the plane which makes an angle 45 to the longitudinal axis. So it looks like a helical fracture. Now we look into the differences between the tension and torsion. What are the differences and similarities between the tension and torsion? So the convenient means of representing the state of stress of an element, it is by means of equivalent stress, which is also known as effective stress or representative stress. Effective equivalent stress, that is sigma bar. Similarly, for the case of strains, it can be represented in terms of the effective or equivalent or representative strain, which is given by epsilon bar. Now from the maximum shear stress criteria, we have equivalent stress is equal to sigma 1 minus sigma 3. This is for the state of stress for the case of maximum shear stress criteria. And for the case of distortion energy criteria or von Mises criteria, equivalent stress or effective stress is equal to 1 by root 2 times of difference between the normal stresses, principal stresses, sigma 1 minus sigma 2 square, sigma 2 minus sigma 3, and sigma 3 minus sigma 1 square root. This is for the case of state of stress. For the case of strains, we have, for the maximum shear stress criteria, equivalent or the effective strain is equal to epsilon 1 minus epsilon 3, and for the case of von Mises criteria, equivalent strain is equal to root 2 by 3 into epsilon 1 minus 2 square, epsilon 2 minus epsilon 3 whole square plus epsilon 3 minus epsilon 1 whole square whole power half. So this is the means of representing the state of stress or strain, a convenient method to represent the state of stress or state of strain of an element by means of effective or equivalent stress or effective strains or equivalent strains, by means of maximum shear stress criteria and by means of von Mises criteria. Now tension and torsion are somewhat, one value can be, or some of the properties, they can be obtained from that of the other for the case of similar materials. So one graph can be constructed from the other graph for the case of same material, either from tension or from the torsion test. So the state of stress for the case of tension is uniaxial, where sigma 1 is the principal stress, and this is also the effective stress or the equivalent stress, because stress in the other two directions, sigma 2 is equal to sigma 3, is 0. So substituting these values into the von Mises criteria, we have sigma 1 is equal to the equivalent stress. So for this is for the case of tension. For the case of tension, we have the uniaxial stress is the principal stress, as well as this is the effective or equivalent stress. By substituting these values, sigma 1 and sigma 2 is equal to sigma 3 is equal to 0 into the von Mises criteria, we have sigma 1 is equal to sigma bar, that is the equivalent stress. For the case of torsion, the thinning caused by the normal tensile stress is countered by thickening caused by the normal compressive stress. Sigma 1 is equal to minus of sigma 3, whereas sigma 2, the intermediate stress, is 0. So substituting these in the case of von Mises criteria, we have equivalent stress is equal to root 3 times of sigma 1. This is for the case of torsion, whereas sigma 1 is equal to sigma bar, this is the case for tension test. Now sigma 1 is equal to sigma max by 2. That is for the case of tension test. When substituting this in maximum shear stress criteria, we have equivalent stress is equal to sigma 1 minus sigma 3. So sigma 1 is equal to sigma max by 2, which is also equal in magnitude, that is tau max. Whereas in the case of torsion test, we have maximum shear stress is equal to sigma max. Tau max is equal to sigma 1 minus sigma 3 by 2. So for the case of tension test, sigma 1 is the principal normal stress and sigma 3 is equal to 0. So tau max is equal to sigma max by 2 for the case of tension test. And for the case of torsion, we have sigma 1 is equal to minus of sigma 3. So tau max is equal to sigma 1 minus sigma 1 by 2 is equal to 2 times of sigma 1 by 2. So tau max is equal to the maximum value of the normal stress. So this is for the case of torsion. Now coming into the equivalent strains. For the case of tension test, we have epsilon maximum is equal to epsilon 1. And in the other two directions, epsilon 2 is equal to epsilon 3, that is minus epsilon 1 by 2. This is for the case of tension test. And for the case of torsion, we have epsilon 1 is equal to minus of epsilon 3, where epsilon 2 is equal to 0. This is for the case of thin-walled tubular sections. For the case of thin-walled tubular section, there is no strain along the intermediate direction. Epsilon 2 is equal to 0. So the state of stress for the case of thin-walled tubular section is both a plane stress situation as well as plane strain situation, because the state of stress is biaxial, sigma 1 and minus of sigma 3, that is tensile and compressive. Sigma 1 is equal to minus of sigma 3, where the intermediate stress is 0. And for the case of thin wall tubular section, it is hollow tube. We have strain epsilon 1 is equal to minus of epsilon 3, and in the other direction it is 0. So this situation is similar to that of plane strain and plane stress, where plane strain is strain along one direction is 0, and plane stress is stress along one direction is 0. So for this case of thin wall tubular section, stress along the intermediate direction, along the second direction, sigma 2 is 0, and the strain along the thickness direction is 0, that is epsilon 2 is equal to 0. So this is for the case of torsion. So once summarizing the differences between the tension and torsion, we have sigma 1, it is the uniaxial tension test. So sigma 1 is equal to sigma maximum, and 2 and 3 in the other directions we have 0 stress. Whereas torsion, it is a state of biaxial. Sigma 1 is equal to minus of sigma 3. And maximum shear stress, tau max, is equal to sigma max by 2. Whereas in the case of torsion, tau max, maximum shear stress, is equal to the maximum normal stress. And for the case of strains, maximum strain is equal to epsilon 1, and in the other directions we have epsilon 2 is equal to 3 is equal to minus of epsilon 1 by 2. And for the case of torsion, we have epsilon 1 is equal to minus of epsilon 3, and 2 is equal to 0. This is for the case of thin walled tube. And the effective stress or the equivalent stress is equal to the principal stress or the normal stress, and the effective stress or the representative stress or equivalent stress is equal to √3 times of sigma 1. Effective strain is equal to epsilon 1, and here the effective strain or equivalent strain is equal to 2 by √3 times of epsilon 1. So these are certain differences between the tension and torsion. So these are the certain observations that were made with respect to the state of stress and the state of strain in the case of tension and torsion. In the case of torsion, large plastic strains can be obtained without the problems like that of necking in the case of tension and barreling in the case of compression. And this torsion test, they can be conducted at high strain rates. So for a case of material, tool steel, when it is subjected to both tension and torsion, this is for the case of torsion, this is for the case of tension. For the case of tool steel, which is brittle when it is tested under tension, because the maximum normal stress for fracture has reached before the maximum shear stress to cause plastic deformation when this material is tested in tension. When the same material it is tested in torsion, the maximum shear stress to cause plastic deformation, it has reached before the maximum normal stress to cause fracture. So this is one of the differences between the tension and torsion. When a brittle, where a material which failed by means of brittle in the case of tension, and in the case of torsion it has reached the critical value of shear stress to cause plastic deformation before reaching the critical value for failure. Brittle materials like ceramics, carbides, they cannot be normally tested under tension because it is very difficult to prepare the specimen to dimensions. It is very difficult to clamp the specimen because improper clamping may lead to failure, as well as there will be certain variation in the stress if they are not clamped properly. As well as these brittle materials, they are very sensitive to defects like notches, cracks, etc. So these materials, they are tested by means of bend test, which is also known as flexure test. Bend or flexure. So these materials, they are subjected to either bend test, which is also known as flexure. So a rectangular material which is supported at its ends and it is loaded at one point at the center. So this material is subjected to bending. So this is known as 3-point bend test. Whereas if the component is subjected to loading at 2 points, it is called 4-point bend test. It is also known as pure bending. 4-point bend test when the component it is loaded at 2 points. The component it is similarly supported at both the ends and it is loaded at 2 points. So this type of testing method is known as 4-point bend test. So from this one can calculate the stress required to cause failure or rupture, which is known as transverse modular strength or modulus of rupture, that is given by capital M, which is the bending moment, and C, it is the distance from the center of the specimen to the surface, or it is 1/2 of the thickness of the specimen. So that is C by I, that is moment of inertia. N is for bending moment, C is half of the thickness of the component or distance from the center to that of the surface, and I is the moment of inertia. So now the difference between the 3-point bend test and 4-point bend test is, once we draw the bending moment diagrams for the case of 3-point, the maximum stress it is at the center. This is a rectangular specimen. When tested under single load, that is the 3-point bend test, the maximum bending moment is at the center. Whereas for the case of 4-point bend test, the stress is constant between the 2 points. The stress is constant between these 2 points, but the maximum stress is similar to that of 3-point bend test. If the other parameters are maintained constant, then the maximum stress is equal to that of 3-point bend test, but it is constant between these 2 points. So this is the bending moment diagram for the case of 3-point bend test, where it is maximum at the center, and 4-point bend test where it is constant between the 2 loading points. For the case of 4-point bend test, there is a large probability for the modulus of rupture. It is slightly lower than for the case of 3-point bend test. The reason is the volume between these 2 loading points, it is larger. So there is more possibility of defects present in this large volume when considered to the small volume under the single load in the case of 3-point bend test. So this may lead to low values of modulus of rupture in the case of 4-point bend test, and it is also proved experimentally. As well as there is more scatter in the case of 3-point bend test. The results obtained from the 3-point bend test, they are subjected to more scatter when compared to 4-point bend test, because the small volume underneath the single point loading, it is more sensitive to defects when compared to the large volume of the weakest portion present in the large volume. So this is the reason why this 3-point bend test, the results, they are subjected to more scatter when compared to 4-point bend test. So these are some of the differences between the 3-point bend test and 4-point bend test. Now we shall see some video with respect to the bending, that is the 3-point bend test. And moreover, when the component is subjected to bending in the case of 3-point bend test, the upper surface is subjected to compression and the lower surface it is subjected to tension. When this component is subjected to bending, the upper surface is subjected to compression and lower surface it is subjected to tension. And at the center there is neither compression or tension, and this is known as neutral axis, where the elements or the fibers at the center, at the mid, they are neither subjected to tension nor compression.